I'm Michael Andrews, co-founder and chief architect of Impira, a database for unstructured documents. I'm here to talk about how we use incremental query execution to power the machine learning necessary for dealing with unstructured data, and in particular for accessing data that's trapped inside PDF documents like invoices, financial statements, and order forms. Working with unstructured data isn't a new problem, and I think probably since the moment the first PDF was created, fans of structured data have been trying to pull data out of them. There are plenty of other options for extracting this kind of data, ranging from pre-baked ML models to end-to-end solutions for specific document types, to all the messy building blocks needed for someone to engineer their own solution. In all these approaches, though, the result is pretty rigid and takes a lot of control out of the hands of the person who's actually going to be using the data. So we're trying something that hasn't been explored nearly as deeply, applying database technology directly to the problem. Before we dive too deeply into the technical details, I'd like to set the scene a little bit about what I mean when I say that Impira is a database for unstructured documents. Now, in a traditional extraction scenario, users like to treat ML models as these immutable, opaque functions, or at least as functions that don't change very often. They'll typically run a model on all of their documents, then insert the results of that transformation into some database system or index to query later. By doing this, though, they're making a lot of important information that's available in the downstream system, such as the final schema of the data, the corrections that have been made, related data that might be in other tables. They're making all this information completely inaccessible to the model. On top of that, they're basically assuming that however well the model did the first time it ran is the best it's ever going to do. There's no opportunity for the model to go back and refine its predictions as it gets new information. To switch that relationship around, we've decided to push all of this into the database layer. What you're looking at now is Impira's UI, where hopefully one of the first things you notice is that we've laid out the data exactly as it exists in the database. Impira has a column type called file, where you can insert your blobs of unstructured data, and from there, you can add whatever kinds of fields you want, data fields and expression fields and join fields, as well as a new kind of field called an extraction field. This is a computed field where the value for each row is derived from a model that's learned in real time from the full dataset. It's basically a machine-learned index, complete with confidence values indicated by the orange and green colors on these cells you can see on a few fields that I've already set up. Adding these extraction fields for PDFs is easiest to do through the UI, but it can be done directly over the API too. And what I think is one of the slickest features this enables is that each piece of feedback goes right back into the model, which can then refine its predictions on all the other documents. In this case, you can see it's predicting values for the new field and repredicting values for the old one. Those of you who are paying very close attention may have even noticed that this prediction in the last name column here just updated with the correct value and became green. Why is any of this necessary though? Machine learning models are getting better and better by the year, so you're probably wondering if there isn't some off-the-shelf model that can just extract all of those fields perfectly. I've already tried some models on the documents in that collection, and they don't do as well as you might hope. We've also tried exposing the results of some pre-baked models directly to users, and people usually just don't know what to do when the predictions are wrong. They can go and correct each incorrect value, but without that feedback improving the model, it ends up feeling a lot like the manual document labeling they were trying to avoid in the first place. And even more importantly than all of that, there's no model out there that's going to do perfectly on every single document shape a user might want to process. The types of documents people create tend to be just as varied as the different kinds of database records that people create. In other words, until we have a system that's as flexible and generic as a database is for structured data, we won't be able to handle the full breadth of different kinds of documents that exist in the real world. Cool, so how does it work though? Users have really loved the ability to refine and train their own models with quick iteration and reactive updates, but making a system like this operate in real time presents a lot of challenges. Let's talk about exactly what needs to happen in the background to power an experience like that. And to keep things simple for now, I'm just going to talk in terms of the model and in terms of events happening in the system, then what we do in response to these different events. In the case of an extraction field, we've broken the work down into a couple different processes, each of which is listening for some input events, performing some work, and then writing its results back somewhere. The first step, we call it training, is responsible for observing any feedback the user is giving, usually in the form of new labels or corrected or confirmed values like you saw me do. And then it trains or retrains a new version of the model that takes those into account. For now, we actually retrain the model on the entire data set when a new label comes in, but we're pretty excited about applying feedback incrementally within the model as well. Either way, evaluation is then listening for new model versions from training and newly uploaded files from the file collection, and then applying the latest version of the model to any rows without predictions or with out-of-date predictions. The model itself is built on a technique called stochastic variational inference, which is designed to operate on very little feedback. Sometimes as little as a single label is enough for the model to learn how to extract a field from your document set. The results of running the model are written directly back to the view the user is looking at, and because this is all happening within the database, they're immediately available to any downstream queries or views or exports. Now, what's nice about framing the problem this way is that each component of the system is only responsible for doing work when something it cares about has changed. For example, when I upload a new file to the system, training actually doesn't do anything at all. It's only listening for new labels coming in. Evaluation, on the other hand, was listening for new files as well as new model versions, so it knows to wake up and generate some predictions. So, in order to power these different processes, we need a system that can recognize changes in real time, route them, schedule some work to perform some kind of translation, and then update a result set based on those changes. Many of you have probably encountered this feature before, and in database systems, this is referred to as an incremental materialized view. It's not a new technique in the world of databases, but actually surprisingly few databases have implemented it and really take advantage of it. Now, Impira has borrowed and stolen database components from other systems wherever we can, in particular for storage, but we've specifically decided to implement our own query processing layer and versioning system, firstly so that we can tailor them to work with the new concepts you just saw, like file fields and extraction fields, but also so that we could implement incremental execution for all queries supported in the system. Our query processing functions on a simple proprietary language we've created called IQL. It's designed to be pretty powerful. It supports joins and subqueries and group bys and things like that, while remaining simple enough that we can reasonably support it ourselves, including having incremental execution as a first-class feature. I've written out a simple query here, which is projecting out just a couple of columns from that collection of files we looked at earlier, and I can run it directly, or I can use incremental execution to turn the query into an event stream by looking at how it changes over time. What you're seeing now is a set of timestamps on the left here, increasing from the bottom, and then the changes that happen to that query for each timestamp on the right. In this case, you can see the moment where I gave the label, followed by a number of repredictions on rows of the table, including the moment where the model adjusted its prediction as a result. Because I'm only projecting out that single field, none of the edits or predictions happening in other fields are showing up as events for this query. And the queries that we run for training and evaluation are a little more complicated than this, but they aren't that much more complicated. The coolest part about all this, to me at least, is that it's incredibly easy to change those queries as we want to incorporate other kinds of inputs to training or evaluation, or to build new types of models. We can also quickly build out other new features that have nothing to do with machine learning, like the live updates you saw in our UI, continuous exports, webhooks, and automatically routing files within the system. Since all of this is available via IQL, our users can even do all of that too. So if we'd built a system that passed events around without having a general way to perform incremental execution, none of that would be possible, and we'd be giving up on a lot of useful generality. Hopefully this is giving people other ideas about how this technique can be used for a lot of different kinds of real-time machine learning. And for me, the ability to access machine learning primitives from the database opens up a world of possibilities like user-defined models, joining documents on learned properties like visual similarity, automatically detecting how different documents relate to each other, and on and on and on. We haven't done any of that stuff yet, but I'm really excited for us to get there, and I believe that incremental execution provides a strong foundation for when we do. And that's it. Thanks so much for listening, and I'll be around later during the breaks with a couple other members of our team to chat. See ya!